Last but not least, Shaikha, are you here? I guess she's just getting her slides set up at the back. But Shaikha is currently an assistant professor at the United Arab Emirates University. I believe she did her PhD there as well, and went on to become an assistant professor. I understand that she works on MOFs, but today, on top of that, she'll be talking about framework materials for remediation, detection, and therapeutic delivery. So please join me in welcoming her.
Good morning. Thank you very much for coming. It's a great pleasure to be with you today. I am Dr. Shaikha Neyadi from Chemistry Department, UAE University. Since 2022, my research focused in design and synthesis of smart material for environmental remediation, chemical detection, and therapeutic application. Today, I'm very excited to share with you some key findings of our works. And here is the outline for today. We will see first what are the smart material, the design principle and material engineering. Then I will share with you 2 examples from our work in environmental remediation, followed by chemical detection, and I will conclude that with a therapeutic application. As you know, the water, the environment, and health are interconnected. The current material is designed for one application only. So there is any need for smart, selective, sensitive, and multi-application material. And for that reason, the smart material is born. 2 main smart material that we have is the metal organic framework and covalent organic framework. The signature about this material that they are characterized by high surface area, high porosity, modular and tunable chemistry. Response also to the external stimuli like the pH and the light. Actually, the design philosophy behind the smart material is the correct choosing of the linker, the metal, and also functionalize this material with responsive to the external stimuli. So if you choose the correct linker with a suitable metal, you are generating particular pore size that could be used for specific application and function. What I want to say that any change at molecular level will reflect highly in the function and the application of this smart material. And now let me share with you 2 examples from our works as application for smart material in environmental remediation. Actually, in our lab, we try to custom synthesize the linker or the building blocks for the COF that we use it to capture organic pollutant or emerging pollutant, such as perfluorooctanic acid, iodine, pesticide, microplastic, and other. The idea that we try to custom synthesize the linker in order to have a function group, this function group will be able to interact with the pollutant in order to enhance the absorption capacity, and also we keep in our consideration the other factors, such as high surface area, high porosity, thermal and chemical stability of the COF, in addition to recyclability and selectivity. Today, I will talk about 2 pollutants, which is perfluorooctanic acid and the iodine. For the iodine application, we synthesize MA-COF, and this is why this is the first COF that I synthesize, which is MA-COF, from the 2 building blocks. The first one is the phosphazine aldehyde, and the second one is the pyrene amine. In order to produce a COF, this COF will be electron-rich system that containing aromatic rings and heteroatom will be able to capture the iodine. And in order to make this COF more practical and more flexibility, we integrate it with a polymer in order to convert it from powder form into the membrane form. And this is what we come up with. The iodine fiber uptake was around, for the hybrid material, it's around 10.5 gram per gram when we compare it with the COF alone, which is 9.4 gram per gram. And this happened within 10 minutes at 80 degrees. Also in this study, we tried to prepare a different ratio of the membrane between the COF and polymer, and we found also that when we have double amount of the COF, we have the high adsorption capacity, which confirms the role of the COF. Also, the same behavior we notice when we also use this hybrid material membrane to capture the iodine from the solution. As you see here, that the hybrid material or the membrane change from the yellow into the black after absorption of the iodine, and the highest removal efficiency was around 97% within 5 hours. The hybrid material also show a good recyclability and retain its efficiency by 95% after 5 cycles, and also show a good selectivity for the iodine when we compare it with other compounds like water, ethanol, and cyclohexane. The mechanism behind the adsorption of the iodine here, it's visosorption and chemosorption, and we confirm that by using a 3 spectroscopic technique: the FTIR, the Raman, and the XPS. In the FTIR, we notice that there is a clear shift in the peaks of the cuff, which confirm that there is a change in electronic environment. More importantly, the amine bond of the cuff was before adsorption at around 1625, shifted to 1633 after adsorption, which confer the participation and also the interaction of this function group with the iodine. In the Raman spectroscopy, after adsorption, we noticed also 2 new peaks emerging at 167 and 108, and these 2 peaks is characteristic for iodine molecules. Also, the XPS confirmed that the mechanism goes through charge transfer, and this by the presence of the polyiodide molecules, which is the stable form of the iodine. And now I will transfer to the second pollutant, which is perfluorooctanic acid. As you know, the perfluorooctanic acid is anionic pollutant. So for that purpose, we start to design a cuff, starting from the custom synthesis of the linker here, that containing secondary and tertiary amine. This amine, we reacted with different aldehyde in order to produce a series of HKN cuff. After that, also we integrated with Kutasan polymer, not only to give it flexibility, but also the function group in the polymer will enhance and increase the adsorption capacity for the perfluorooctanic acid. What happened here is that at around from pH 5 to 7, the amino group in the polymer will be protonated, which enhance the adsorption of the anionic pollutant perfluorooctanic acid. Actually, the driving force behind the adsorption of this pollutant is the function group that present in the polymer, the function group that present in the cuff, that interact with the anionic pollutant perfluorooctanic acid. And we found that adsorption capacity for the 4 cuff was ranging from 1,000 to 2,500 within 60 minutes. Also, we noticed also that the hybrid material also show high recyclability and retain its efficiency by 75 to 80% after 5 cycles. In this study also, we tried to study the best regeneration solvent to generate the pollutant perfluorooctanic acid, and we try with ethanol, sodium chloride, and a mixture of these 2 solvents. We found that when we have a system that it's a mixture between the sodium chloride and ethanol, give us the best high percentage of the regeneration. And if you look to this video that show reversible swelling, actually we do this experiment. The membrane of hybrid material, we immerse it in perfluorooctanic acid, and after 2 minutes of adsorption, the membrane expand double its size. Okay, maybe you'll see now, you'll see it's expand double its size in order to allow more adsorption for the molecules perfluorooctanic acid. Then it's back to its original size when we immerse it in the regeneration solvent, which is the sodium chloride with ethanol. And this behavior or this response is reversible. Also, the hybrid material show a good selectivity for the perfluorooctanic acid over the other perfluoroalkyl substance. And this may be consistent with the result that we found it from the pore distribution data, where the pore size of the cuff are ranging between 11 angstrom to the 18 angstrom, which is matching the dimension of the pollutant that we found in the literature, which is around 11 angstrom. The mechanism also behind the absorption of the perfluorooctanic acid, as I mentioned before, it's depend mostly in electrostatic interaction, hydrogen bonding, hydrophobic interaction between the function group of the polymer, the function group of the cough, with the pollutant. And here are two evidence that support the absorption of the perfluorooctanic acid that we run it, which is the FTIR and the XPS, before and after absorption. In the FTIR, we note that there is 3 new peaks. The first 2 peaks are at around 1,100 and 1,200, which is corresponded to CF2 and CF3 for the pollutant. And the last peak is the new carbonyl group, which is at around 1695, which is corresponded to the carbonyl group of the perfluorooctanic acid. While in the XPS, after absorption, there is a new peaks for the fluorine. So both IR and the XPS confirm the absorption of the perfluorooctanic acid. And now I will transfer to the second part of my presentation, which is the chemical detection. If you remember, the MACOF that we synthesized it to capture the iodine from the solution and the vapor, this COF actually also works as a selective, sensitive fluorescence chemosensor for the HCl vapor. So it has a multi-application. If you look to this video, you will see that when we immerse the hybrid materials in the HCl vapor, it changes its color from the orange to the black. And this response is reversible when we immerse it in triethylamine, which confirms its reusability. If you look also to the fluorescence measurement, you will see that there is a clear shift in the peaks, and the new peaks is increasing by increasing the concentration of the HCl. Another application also for the chemical detection is the BT-COF. BT-COF was synthesized from a 2 linker, which is the phosphazine aldehyde and triazine linker, in order to produce a COF which is rich in the nitrogen. The idea of preparing this COF was to capture the lead, which is one of the heavy metal. The interesting that we notice that when this COF is capturing the lead, it's changed its color from the yellow to the brown, as you see in this simulation video. Also, the color of the COF back again to its original color once we make the desorption with the HCl. Not only that, but the BT-COF also show a good selectivity for the lead over the other metal, and show also high sensitivity, where only the concentration of 0.01 ppm of the lead can cause shift and changing in the color. Also, the BT-COF show high absorption capacity for the lead, and it was around 940 milligram per gram within 20 minutes. And now let's go to the last part of my presentation, which is the therapeutic application for the smart material. Actually, in my PhD, I synthesized 2 drugs for treating diabetes type 2. And these 2 drugs are working with different mechanisms. The first one works as oral GLP drug, and I call it Novapair. And the second drug is C7, and work also as metformin analog. Both drug is patented drug, and also both drugs show promising in vivo and in vitro result. And in order to increase the bioavailability of this drug, and also enhance the drug release profile, okay, I try to encapsulate them in ZIF-8, then I coat it with sodium alginate. And now I will start to tell you the story about the first drug, which is the Novapair. Novapair is the first oral GLP drug for treating diabetes type 2. As you know that there is 1 million of diabetic people around in UAE. And also there is 500 million people around the world. They inject themselves every day, every week, just to stay alive. Costing billion to trillion every year. Big number, big cost, and a big need. Oral GLP drug can change that. For 1 million of people, controlling diabetes is not just controlling the blood sugar, but also controlling the pain. The current GLP drugs are injectable, uncomfortable, and it's hard to keep it up. Most of the patients, by the time, stop them. With Novapair, we are transforming the diabetes care from the injection to the tablet. no injection, no needles, no painful, no refrigerator, no drop-in efficiency. Just convert, control, and convince. And here is the story. The story started that we encapsulated the Nova pair in ZIF-8, then we coat it with sodium iliginate. I hope it's worked, the video. No? Okay. When I coat it with sodium iliginate, this polymer will protect the formulation and protect the drug from releasing in the acidic medium, which is in the stomach. Once the formulation reaches to the intensive, excellent. When the formulation reaches to the intestine, where the pH is 8, the sodium iliginate starts to dissolve and breaking down. Then the ZIF-8 will be exposed to the fluid of the intestine that containing the phosphate and the carbonate. This ion will coordinate with the zinc, which is in the framework of the ZIF-8, and try to weaken the bond between the zinc and the nitrogen, which result in breaking down the ZIF-8 also, and control the release for the drug Nova pair, which result in controlling the blood sugar. The idea that the sodium iliginate, it consists from carboxylate group. So in the acidic medium in the stomach, nothing will be happen. When this formulation reaches to the intestine where the pH is 8, the carboxylate group will be deprotonated, charge will be negative, and there is repulsion between them, which result from dissolving of the iliginate and also destroy the ZIF-8, and also then it will be released for the drug Nova pair. And the releasing happen within 8 hours. And this is exactly the construction of our formulation. Okay, it consists from the Nova pair, which is the pyrimidine drug. Then I coat it with the ZIF-8, which is known as its low toxicity, high porosity, and also high surface area, and also consists of the zinc. Zinc, it's known with its reduced its oxidative stress, and also it has anti-diabetic properties. After that, I coat it with sodium iliginate, which is biodegradable polymer, stable at acidic medium, and also unstable, or it will dissolve in basic condition. Together, the sodium iliginate, the ZIF-8, the zinc, and the Nova pair collaborate together in order to produce promising oral GLP drug for treating diabetes type 2. And now let me share with you the drug release study. And we notice that when we have uncoated formulation here, or uncoated sodium iliginate, the drug will be released in acidic and basic condition. While when we have a sodium iliginate, as you see here, we have low release for the drug at acidic medium, which is in the stomach, but we have controlled release in the basic condition, where's the target area. Also, I'm sharing with you the in vitro study here. It's clear here when we have the basal condition, where there is no glucose, the Nova pair, it has low insulin secretion, which is very positive in order to prevent the hypoglycemia. But in glucose simulation, you will see that the Nova pair increase the insulin secretion in controlled, in dose-dependent form, and also in the behavior, better than the injectable drug. Also, the in the in vivo results show that the Nova pair also decrease the blood sugar from 400 milligram per DL to 100, mostly 100 within 5 hours, and this is the behavior for the oral drug. After we succeed with the Nova pair, I tried also to encapsulate the C7, which work as metformin analog at the same formulation. As you know, the metformin is the first line to treat the diabetes, but it has some limitation, such as low bioavailability, side effect, and also it's required high dose. So I tried to encapsulate the C7 in the same formulation, and this is what we'll come up with. For the drug release profile, we have the same result, and I will share with you the in vivo result. The in vivo result here show that our formulation, lowering the fasting glucose and also lowering the post-glucose, lowering the production of the glycogen from the liver, and the most interesting thing, that it's increased the sensitivity to the insulin. also reduce the insulin resistance. In general, the C7 formulation show a better result than the metformin. Also, there is no weight loss or no toxicity was observed. And let me discuss with you 3 parameters here. The first one is the fasting blood glucose. You will see here 4 groups. The first one, which is the normal control, which is the healthier animal. In the second column, it's the diabetic animal without any treatment. And the last column, the third column here is the metformin when we treat the diabetic animal. And we note, if you see here, there is a reduction in the fasting glucose. But the most interesting thing that when we use C7 formulation, the reduction here is very strong compared with the metformin. Also, we test 2 parameters, and you will see here also the C7 lowering the glycogen, which is a production from the liver, and also show a good long-term glucose control, or it's keep the glucose level for 2 to 3 months. So all this in vivo study confirmed that the C7 formulation could be used as metformin analogs to treat diabetes type 2. And during the last minutes, I share with you how smart material is used in environmental remediation, chemical detection, and therapeutics application. Nothing will be done without my hard working of my undergraduate student. So thank you very much for them. And also thank you for UAE University, and thank you for your attention.